before I record, exam was easy, right?
Yes.
Okay. There was no any problem with the exam, basically. If there is no any problem with the exam and everybody understand what is FSM, so people are ready for what? Working with counters and also registers and also building ALU. So there's a counters, there's registers, and ALU. Sounds good?
Yep.
And the registers have something as a special case called shifting register. Under shifting register, there is a bunch of configuration. What is this configuration? There is SISO, SIPO, PISO, PIPO. What are those? This one is the serial input, serial output, or serial input, parallel output. There was another one which is called parallel input, serial output, and the last one you can guess, which is going to be parallel input, parallel output. We're going to learn all of these things, okay? For the counters, we have two things we're going to learn about. Something is called asynchronized counter, and there's another one is called synchronized counter, okay? And then no matter what, we're going to have something is called up counter, there is down counter, and there is another one is called modular counter. And there is one I invented, which is teasing everybody because, you know, it's a little bit tricky. It's called a regular counter. So that's basically what we have left in this course. ALU is just a bunch of whatever we learned so far. So any question regarding the map for reaching the ending point of this semester?
Are we going to get into Verlog at all?
Do you want?
I don't know. We're just asking.
Yes.
My question, if you want, I can do it. If you don't want, I can
yeah, maybe just like a nice little intro.
Yeah, but it will not be counted in exam because I don't want to be too much on you guys because, you know, maybe some people, they don't have enough, like, you know, they don't have the computers to will host the Vivado and stuff like that, you know what I mean? Technicality, you know, you guys are, I didn't ask you to buy whatever stuff in the beginning, right?
Yes.
So I'll just give you a little bit information, okay?
Sounds good.
Okay, sounds fair and good. Okay, I would tell you that, you know, I'm gonna do my best for grading, but you guys know my story. I'm not teaching just 2300, I'm teaching other classes, and, you know, I'm the only person who is actually grading all of this stuff because I don't like TAs to grade my stuff. I like to do it by myself, to be fair. So I will do my best. And of course, I will ask my assistant, which is the AI model I use in the Gradescope, to help me, okay? Anyway, now we're gonna start with counter, right? We said we have counters based on synchronized or asynchronized, right? So if we're gonna start with synchronous counter, in the beginning, what does the counter mean? What does it mean, counter? Somebody can tell me what does the counter mean? Nobody want to tell me? It counts. Yes, it counts. It counts based on what? It counts based on what? Huh? It counts based on a step of time, a step of something. So for instance, in C, how do we count? We will first define something, right? Like int CNT equals 0, right? So we define something called CNT and we initialize it with 0. So that means, culturally, counter, it has to have initial state, right? Starting from 0. Then we say Synch is equal Synch plus 1. So that means every single time I will be accumulating 1 in the top of the present state to bring the next state. That makes sense? I can remove this one and I call it a step. And I can define the step. That makes sense? So how can we look to the counter? So basically, if I say synchronized counters, so I need to believe in one thing that, my counter will be built using what? The elements we learn from the sequential circuit perspective, which is what? Flip-flops. So we're gonna use the flip-flops to build the counter. And when I say synchronized, that means every single increase by steps, yes. So every single flip-flop will be used for building that counter. It will be tied to the same clock. Again, let's say that, I would like to have a 3-bit counter. So that's something, famous, 3-bit counter. When I say 3-bit counter, that means there is 3 flip-flops will be used to implement such a counter. And of course, based on how many bits, which is the flip-flops I have, I can define how many states this counter will pass. That makes sense? So if I say 3-bit counter, so end of the day, I'm talking about 2 power 3 states, which is starting from 0 to 7. So this counter will count 8 states starting from 0 to 7. How did I do it? Number of bits are used for the counting will be associated, since we are in a binary, so gonna be 2 power this number. So end of the day, gonna be what? 0 to 7, that means 8 states. So if somebody tell you that I have a 5-bit counter, 5-bit counter. In a 5-bit counter, end of the day, I'm gonna be 2 power 5 states. So that means it's gonna be 32 states. And that will be translated to 0 to 31 if I am up counter. So we defined how can we translate number of states in the counter based on how many bits or basically flip-flops are implemented or using to implement this counter. And now we're gonna go into the type of the counter. So the counter can be up counter or down counter or modular counter, or as I called irregular counter. So what are those? So if I say I have 3-bit up counter, so I'm actually talking about my initial state is 0, and I'm start incrementing in the top of the 0 to reach the maximum state, which is gonna be filling all of the bits with 1. In that case, 3, so they're gonna be 1, 1, 1, which is translated to 7. So I count 0, after that 1, 2, 3, 4, 5, 6, and 7. Do you guys agree? While in a down counter, I start with the maximum state I can reach to be the initial state. So it means that, if it's 3-bit, so I'm gonna start from 7 and I start decrement. So gonna be 7, 6, 5, 4, 3, 2, 1, and 0. Then I return it back to 7, and so on. They call it ring counter. It's a ring at the end of the day. I cannot go outside the boundaries I already set. For the modulo is a little bit tricky. Why? Because imagine that I have a 3-bit counter. So that means, you know, my counter is counting from 0 to what?
7.
7. But then I decided to say, no, I would like to count on 5. So I'm going to say that it's going to be modulo 5. But I know I'm 3-bit. So what does it mean? It means that if I'm up, I'm going to be 0, 1, 2, 3, 4. And after that, what will happen? I will never see 5. So 5 here, it means how many states I can reach, right? So then I can go back into what? 0. So I cannot see 5, 6, 7. Right? That will help us later to define something that's called reset. So since I'm a sequential circuit, and my sequential circuit have a starting state based on what type of counting we are doing. So end of the day, we have to have something to a starting point, like a pointer point to the point in the first state. And we call this what? Reset. So we have reset. So the example, for instance, if I'm a 3-bit up counter, 3-bit up counter, so that means it's up counter. So that means if I reset, I go to state 0. That makes sense? If I reset in a 3-bit down counter, I will go to state what? 7. So far, so good? Huh? Hello?
I'm just trying to understand. So is the reset part of the module 5?
It's not module. It's what do you mean by module? Modulo or what?
Yeah, modulo 5, right? That's
it's not modulo. It's about
so
any counter. Any counter has initial.
Then I need to make some sort of connection with Arthur through shared memory.
Yes.
Any counter has initial state. Do you agree?
To take that data and
the reset is the initial state layer.
Okay, got it.
So you know, it's like, you know, they call it homing. Do you remember? You know homing, right?
Yes.
So if you already have a rail, right, and you have a sensor in the top of the rail, and I push homing, what will happen to that sensor? It will go to the starting point, even though that I'm in somewhere else. Let's say that I'm in state 5, and I push reset, then I will return it back to 0 as I'm an up counter.
Or if it's down counter, then it will go to 7.
I'll go to 7, yes.
Or whatever the maximum.
Whatever I set it.
Got it.
Make sense?
Mm-hmm.
Anyway, let's tie the counters with whatever we learn in what from finite state machine and flip-flops and all these things, right? But before I do this, I want to show you how the synchronizing works. So we said that the main elements are used for the implementing the synchronized flip-flops is basically what? Flip-flops. Counters is using flip-flops, right? So let's say 3-bit counter, and I want it to be synchronized. So that means, you know, this is my first flip-flop, this is my second flip-flop, and this is my third flip-flop, right? If I claim that my circuit is synchronized, so that means, you know, this one connected to this one, connected to this one, all of them are connected to the clock. So that means all of them are share the same clock. So that's called synchronized counter. Okay. While the asynchronized, that means every single clock is different than the other. Make sense?
Yeah.
So we can write here a note. Synchronized flip-flops as example of the counter, right? Means all flip-flops are using the same source of clock. Okay? That's first thing. The second, how can we push the counter to the finite state machine? We learn in the finite state machine that we have the graphical representation, how do you call it in some other resources, diagram, the finite state machine diagram. Do you guys agree? So some resources of information you can receive from internet, it tell you, finite state machine diagram. But in reality, if you want to be very careful, you say it's a graphical representation of the finite state machine, right? So you do it was associated with what? With a state table. Do you guys agree? So if I want to build a state table for 3-bit up counter, and this counter doesn't have any control, just counter. Once I put the clock, it will just keep counting. How I'm gonna do this? So I return it back to the definition of the state table, right? What is the definition of the state table from your point of view? Present, next. You guys agree? Now, this counter, how many bits?
It's a 3-bit.
That means three flip-flops, right? Mm-hmm. So that means, I have here QA, QB, QC, right? Those my present. What is my next? Gonna be Q.
QA star. QA,
yes, sir. So gonna be QA plus, QB plus, QC plus. I can make a plus star. It's up to you, right? Then this table is covering how many states? 8. Because I have here the input 2 power 3, right? Right? So in that case, I will just say here 1, 2, 3, 4, 5, 6, 7, 8, right? 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1. 1, 2, 3, 4, 1, 2, 3, 4. Okay. Now we define this guy to be what? Up counter. You guys agree? So that means every single state will go up above by 1, right? And the step for us is 1. So that means if I'm in the up counter, if my present state is 0, what is my next state?
1.
Thank you. It's going to be 1. Okay, if I'm in 1, my next state will be what? 2. If I'm in 2, my next state will be what? 3. 3 will be 4. 4 will be 5. 5 will be 6. 6 will be 7. 7 will be what?
0.
0, exactly. 1, 2, 3. So what we did now, we already filled the state table for the 3-bit up counter. 3-bit what? Up counter. So far, so good?
Yes.
If I want to translate this to graphical representation, it's a piece of cake. Do you agree?
Yes.
Why? Because, I have 8 states. So in that case, I can make what? State is 0.
8
state
circles.
is 1. Huh?
8 circles.
Exactly. State is 2. State is 3. State is 4. State is 5. State is 6. State is 7, right? And I know what is S0 is 0, 0, 0. S1 is 0, 0, 1, and so on, right? So basically, you can write it like this if you want. You can do that, right? Now, I know my present is S0 is going to the next. What do you think? Cool, right? So what I did now, I built a finite state machine for what?
A counter.
A counter without any control. Just, you know, you connect the crystal with electricity, boom, that counter will be running like this, right? Now, what is my strategy to do implementation? How I'm gonna implement this? So I'm gonna do the same trick we learned before, if you guys remember, excitation table. So I go in this table and I just go ahead like do like this. And literally, if I don't give you an instruction about what flip-flop you use, what is the best flip-flops?
D flip-flop.
T flip-flop.
Oh, it's T?
Yes. So D is used more into data. T is used more into what? Counting, because it flipped when it turned it back to be 1, 1, if you remember. Right? So that's why they call it transition flip-flop. Standing for T is transition. So I can just have to have now TA, TB, and T what? C. You guys remember the excitation table for the TA, TB, and TC with the QQQ? If I remember, it was like an XOR, right?
Yes, it is.
If you don't remember, you know, I do a trick. You want to see the trick? The trick is the following, you know. I know that, you know, my characteristic stick table is basically Q, QA, TA, QA plus, right? 1, 2, 3, 4, right? Now, 0, 1, 0, 1, 0, 0, 1, 1. I remember transition, that means, you know, J and K are connected to the same source as called T, right? So if it's 0, so that means it's gonna be storing. So 0 will be 0. If it's 1, it flipped because it's actually JK 1, 1. So gonna be here 1. Then, you know, if it's 0, it's gonna be the same. If it's 1, it's gonna be reverse. 1, it will be reversed to be 0. I'm reversing this or keeping this. Did you see that? Right? I don't know what the heck was my screen, but it's annoying me, you know? It's like turning off and on you guys. Okay, I was working on. Okay, now if I want to get this into excitation, I will just go ahead and say QA plus TA, right? 1, 2, 3, 4, 0, 1, 0, 1, 0, 0, 1, 1. If I will go and take this from the table, I would find out, you know, when is Q 0 and 0, the output will be 0. If it's Q is 0 and 1, the output will be 1. If it's 1 and 1, that will be 0. If it's 1 and 0, that will be 1. So I'm right. It's an XOR. So do you see, you know, I just remember from the T, you know, from the JK. Now I will go ahead and fill this table. Somebody can help me. You guys should help me. So who would like to help me with QA?
Maybe 0, 0, 0.
It's gonna be 0. It's gonna be 0. And it's gonna be 0. And here it's gonna be what?
1.
1. Here it's gonna be what?
0.
Here it's gonna be what?
0.
Here we're gonna be what?
0.
Here we're gonna be what?
1.
Perfect. Somebody else will help me with TB. 1 second, let me make a different color so you guys will understand. Okay, somebody help. TB, what will be?
0, 1, 0, 1, 0, 1.
Come on, I'm not fast, you know, I'm a slow person. 1, okay.
0, 1, it just alternates the whole time.
1, and then what?
0, 1.
1, okay.
0, 1.
0, 1. Thank you. Somebody else will help me with the last what? is the last flip-flop, huh? It's gonna be what?
1.
1, huh? What else?
0.
You sure?
Oh, I'm sorry. 1, yeah. Or maybe.
Okay. And then
1 or 0.
one is
And
what?
then 1.
This one is what?
1.
This one is
1.
what?
Next one's 1.
This one is what?
1.
This one is what?
1.
This one is what?
1.
Yes.
Awesome.
Awesome, right? Okay, I have a news for you. We finished. So now 3K maps, 3K map of lovely maps. But you know, this map, it will be 3K maps will be made based on what? Those only 3, you know, is not involving the next, right? So I can just go ahead and make, you know, TAK map. They're gonna be QA, QB, QC 0001111001 0132 4 5 7 6, right? Then you know if I go here in TBK map, let's take it one by one so I will not make a mistake. So you know TA, which elements is going in? This one, which is actually 3 and 7, right? 3 and 7, right? Anything else, you know, we should report inside the K-map in this case? No. So here it's gonna be 0, 0, 0, 0, 0, 0. So pretty much you can come and say TA as a function of the QA, QB, and QC equivalent to what? One group, which is the QB ended with the QC. Any question regarding this part? Hello?
Makes sense.
Perfecto. Now we're gonna go into the next in the row. 1, 1, 2, 3, 4, boom. QA, QB, QC, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1. Right? 0, 1, no, 2, 3.
I think you have an extra block.
Yeah, that's, you know, I feel like, you know, I'm doing something wrong, but you know, it seemed that I didn't drink coffee, you know. Scheiße. I destroyed the whole thing, you know. That's really nasty. Oh my gosh. Here, right?
No.
Like
No,
this.
you added another block again.
Really?
Yeah.
I did.
Yeah, that you have 5 blocks.
That's not nice. You know what? I'm tired. I'll just.
It's not good.
It happens, you know.
Yep.
It's a lack of sleep. Anyway, go ahead like this. Boom, boom. Here, 1, 1, 2, 3. Like this. QA, QB, QC, 0, 1, 0, 0.
Yeah, I have the same issues on my exams too.
You did? Okay, see, I'm not the only one. Good.
Well, yeah. I hope you'll take that into account, sir.
No. Come on, you had a exam from 8 o'clock in the morning to midnight, dude. Come on, you know, I just made a mistake and I fixed. Let's go for the K map for B, right? So
yeah, sounds good.
1.
It's it looks like an X4.
1, 3, 1, 3, 5, 7, right?
Oh, maybe not. Never mind.
1, 3, 5, 7. 1, 3, 5, 7, right? 0, 0, 0, 0. So if I do like this, what does it mean?
QC.
It's gonna be this, right? QC. So TB as a function of the QA and QB and QC is equal to QC, right? Now we're gonna go into the last equation. 1, 2, 3. QA, QB, QC, 0, 1, 0, 0, 1, 1, 1, 1, 0, location 0, location 1, location 3, location 2, location 4, location 5, location 7, location 6. If I go into this equation, that's set for ones, right? 1, 1, 1, 1, 1, 1, 1, 1. Right? What does it mean? It means TC is equal what? 1.
0? Oh, 1. Yeah.
Why 0? Why every single state is 1? It's a big bulk like this, right?
Mm-hmm.
Okay, now implementation. It's a piece of cake. Why is it a piece of cake? Because you already have here the flip-flop A, flip-flop B, flip-flop C. And we're gonna assume those guys are what? Are reporting in the positive edge of the clock. Because if reporting in negative edge of the clock, it would be also, it's not a problem, you know what I mean? But anyway, so now I'm gonna use a different color, just like to make it like this. And this is the clock, right? Now we're gonna use QA, sorry, clear. This is TA, QA, right? TB, QB, TC, QC, right? Now we're gonna start collecting. So TA was what? QB, QC, right? QB, QC. So let's have a different color. QB, QC, and they are ended together, right? Then TB is what? Is QC, right? So we can take this. Then TC is what? 1. So this circuit will be counting from 0 to 7. Any question? And what is the count will be? Those guys.
0 to 7. Well, it's a binary.
Those 3 would be taking the output from here, right?
Mm-hmm.
Any question? Now we're gonna start adding more into the circuit. So we said there's something that's called what? Reset, right? And there is enable also. So we can make reset or we can make enable. Which one you guys prefer first? Enable or reset?
Are we using the enable pin on the flip flop?
Yeah, everything is possible in this life, yes.
Sure.
I'm telling you from here, from this point of view, everything is possible.
Sounds good.
Okay, tell me. So the way to do, we can make it enable if you want. Let's make enable first, it's easy. Enable. It is an external signal which is used to determine the movements of the counter from state to other, right? Based on the polarity. What does it mean? If it's 1, I resume. If it's 0, I pause. Make sense? How can we do this in the 3-bit? So if I have each state's 3-bit counter, up counter, right? So I have here S0, I have here S1, I have here S2, I have here S3, I have here S4, I have here S5, I have here S6, I have here S7, right? If I'm working with the enable, let's say I'm in a state 0. So enable has 2 directions. Do you guys agree? Either they're gonna be 0 or 1. Let's say that I'm working in active high. So, my assume active high enable is used to resume the 3-bit up counter activities. Okay, so if my enable is 0, I'm gonna stay as am I, right? So then I can do it like this. Here, enable equals 0. But while I'm in S0, an enable turned to be 1, so that means I'm going to S1. Right? Continue. If my enable in S1 turned to be 0, I'm gonna stay as am I in the state 1. While it turned to be 1, I'm gonna transit to the next state. And so on, whole cases will be identical, right? Is it clear, guys?
Yes.
So the circuit looks very funny, right? You flip in the state or not. Let's translate this into what? Let's translate it to state table. So how I'm gonna do this? That's not very hard. Till now I have QA, QB, QC, and those 3 are present state, right? I have output is gonna be QA plus QB plus QC plus, and those are my next state. But now I have extra input, is called what? Enable, which is actually converting this table to be how many states? How many states this table would be covering?
16.
16. That's correct. So, you know, here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Now gonna be 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Here gonna be 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. You're gonna be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. How gonna work? If it's 0, my present is gonna be the same as the next, right? So my present is what? 0. So I'm gonna stay 0. If it's 1, my present will move to the next. So I will increment. So if my 0 in this case would be what? 1. My present is 1. I'm 0. I'm gonna stay as a myself 1. So I'm gonna be here 1. While if it turned to be 1, so 1 will return it back to be 2. So gonna be 2. Then my present is 2. I'm 0. I'm gonna stay as am I to be 2. So I'm gonna be 2. Then I turn to be 1 while I'm in 2. So I'm gonna move to 3. Then 3, if I'm in 0, I'm gonna be 3. While I'm in 3, I'm enabled 1, it's gonna be 4. Move forward, they're gonna be 4. And they're gonna be 5. And they're gonna be 5. And I'm gonna be here what? 6. I'm gonna be here 6. I'm gonna be here 7. I'm gonna be here what? 7. I'm in 0. I'm gonna turn it back to 7. But I'm in 1. I'm in 0. I'm gonna be what? 0 and I flip. Any question? Hello? Do you guys have any question?
No, sounds pretty simple.
It looks easy peasy lemon squeezy, right? Next step toward the implementation, it will be what? Extended excitation table, right? So you're gonna have here T, A, T, B, T, C, and we know end of the day, we are looking into what? The QA with itself as a next and so on. So, you know, if you go like, you're gonna go like this. Right? Then when I will make the K-map, the K-map will be what end of the day, guys? It will be a 4 variable K-map, right? Involving those 4. And you will make the implementation. Is it clear or do I need to make the implementation?
It's diamond clear.
Huh?
It's clear.
Okay. Any questions so far? Is the subject is clear so far to everybody? If it's clear, please write clear in the chat. Oh, diamond clear. Oh, crystal clear. Oh my goodness, clear. Clear. La, 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 clear. Okay, good. So I'm gonna leave it for you guys. Consider it as a self-homework. Self-homework. Okay, what is the homework? You're gonna continue this table and you will make the K-maps and you make the implementation. Here, homework. So the TA, TB, TC, then apply K-map to get the Boolean equations associated with the 3 flip-flops inputs.
In the K-map for this, we would do QA, QB on one side and then QCE on the other side, right?
What do you think?
That's what I think. Is that right?
I mean, that's my question. So
yeah, I think we start the K-map from left to right, so it'll be QA,
exactly.
QB.
No matter where it's gonna, you have to start from left and right to avoid the orthogonal K-map.
Okay. And then QCE.
You are right. You're gonna go like this.
QCEN, yeah.
So, you know, your K-map would be like this. QA, QB, QCEN. Okay, doke. Subject is very easy, right? Now, what about the reset? So in a reset, if I am in a certain state and I say reset, so that means go back home, right? And my home is the state I initialized with. So up counter, initialized state is what? 0. If you are active high, yes. But if you are active low, what the initial state will be?
One.
Exactly. Watch out because I'm tricky. Okay, so if I'm a 3-bit counter and I name it to be up and I'm using active high, I start from 0, 0, 0, which is also controlled by the reset. Right? How this gonna look like in the state machine, and you guys will continue the rest. So how gonna look like? That's not really hard. Basically, no, I'm in a state S0, state S1, I'm in a state S2, I'm in a state S3, I'm in a state S4, I'm in a state S5, I'm in a state S6, I'm in a state S7, right? Here we go. So if I am resetting on this while I'm in S0, what will happen to me? I'm gonna go back to S0, right? So here.
But isn't S0 considered to be reset?
Yes. So imagine that I'm in 0 and I push reset. What will happen?
So is reset an input?
Yes, it's an external input.
Oh, okay. Reset is okay. Okay.
You want me to write it? It should be external signal. Signal, I call it signal. It's signal actually. Anyway, external input. Okay, so I push the button while I'm in S0, I return it back to S0, right? But you know, if I'm in S0 and there is no reset, automatically the counter will be resumed counting. So in that case, you know, I'm going to what? To the next state. Look at the fun. I'm in S1 and somebody pushes the button. What will happen? I will return it back to 0. But if I'm in 0, I resume. Now I'm in S2 and somebody pushed the button. What will happen? Nobody pushed the button while I'm in 2. Safely, I will go back to what? The next state. I'm in 3. Somebody pushed the button. Nobody pushed the button. I continue. I'm in 4. Somebody pushed the button. Nobody pushed the button. Same thing. Over and over what?
So from okay, yeah, F7, if you press or don't press it, it's because regardless you'll go to
because I resume, right?
Mm-hmm.
Make sense? So your table that you're gonna continue as a homework, self-homework, that means you don't need to report it to me. If there is issues, you can just tell me, okay?
I had a question. So would that, if you fill out the table, wouldn't that give you like an X for S7? It will give you like, oh, it could be 1 or a 0. Yeah, okay.
Right?
Mm-hmm. Yeah, sorry, I just answered my question.
And this table will be 16 states, right? Self-homework. Implement such structure using synchronized flip-flops, particularly D flip-flop. Okay, Doc? Yes.
And we use D flip-flop because it's resetting, correct?
No, it's not because anything. I decided to make it D flip-flop.
Okay.
It is recommended to use T flip-flop, but it's not a rocket science to use any flip-flop.
Okay.
Make sense?
Yeah.
Okay, Doc. So let's summarize what we learned today, and then we'll continue next time. So we start talking about the whole entire lecture started by that. What is still left? We have counters, up counter, down counters, synchronized, asynchronized, right? registers, special cases, up, shifting left and right and rotate left and rotate right, based on the functionality, or based on the configuration, going to be serial in, serial out, parallel in, parallel out, and all these things, right? In functionality, you have shift left, shift right, rotate right, rotate left. That's the functionality. Configuration of those. Okay. Then we said we're gonna talk about a little bit of ALU, and you guys will be some Verilog in the end. There is also something like a use case of finite state machine is very famous. We need to actually go through it. It's called what? Sequence detector. Maybe I can give you some information about sequence detector. So the sequence detector, you guys aware of human DNA? Have you heard about something called DNA?
Like in biology?
Yeah. Okay, let me tell you a historical story. So sequence detector, that means there is a certain, there is a streaming of inputs, and I'm looking for a certain segments of data. If I see it, I want the circuit to tell me one. That means I found. What type of application this can be happens in the communication with satellites. Like I found some sequence of malicious, or like, Trojan, backdoors, all of this security thing. So I need a filter will tell me whether that, there is something from my data patterns is already there, then, I'll catch it, then I change the code or the orientation of the satellite, then, I'm safe. One of the applications, or, I'm looking for a certain streaming to figure out that, the video broadcasted from the right channel. It's broadcasted from CNN, not somebody fake the video and say that it's CNN. I'm looking for the streaming to find the CNN example, right? In biology, you can convert the human sequences, which is called DNA, into sequences of streaming 1 and 0s, and then you were looking for gene, and you were looking for the mutation. If you find this certain sorting sequence, that means this human, for instance, has a possibility of carrying cancer, or having a possibility for losing hair, or has a possibility for getting darker skin or lighter skin, or brown eyes or a green eye, whatever, right? Because you know how the human works, right? The human body. How did you end up having skins and tissues and bones and stuff like that? It's a code written in your blood, and this code called DNA. And basically this DNA is based on 4 bases of carb. It's called carbohydrate. It's called A, T, C, G. Those are the 4 bases you have in your body. Then you have a long strips of sequences like A, T, C, C, A, C, G, da, 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 da. Then they will start unfolding the DNA you have, and you start looking into portion. Oh, this set build his liver like that, give an order to the blood to cluster some of the calcium and some of other stuff to build the organ, and then the organ build tissues, and then after that you will be human, something like that. Okay. So anyway, DNA sequencing is something famous, especially with the pandemic, because they know the virus segmentation, the code of the virus. The virus is not something alive. It's just a code. And this code is a bunch of ATCC, whatever. So they will run all of your DNA, and they will start looking. He has this, oh, he has this, oh, he is positive. Oh, no, he doesn't have negative. Even though that's something now, trying to approve by FDA. Have you guys heard about FDA? Have you heard about FDA? FDA is the organization here in the United States for approving the medications and stuff related to your health. And it's running by NIH, which is National Institute of Health, which is a big, prestigious organization here in the country. And pretty much they are looking for something called genetic treatment. So instead of, for instance, somebody has a cancer, yes. So if you look into somebody has a cancer, what is the best way for you to overcome the cancer? to go ahead and kill the cell, or, you know, cut the cell, like make a surgery, or use a radiation to slow down the cell. But you didn't solve the problem. Why? Because the problem coming from the gene sequencing. So if you go ahead and flip the A instead of C and C instead of A, what you are doing, actually, you are fixing the code. Then you don't need to remove the tissues or making surgeries or, you know, using radiation and chemo and all of this negative stuff. This is something the humans are thinking about how to do it, and scientists, in a way that it will be the future treatment for most of the problems we have these days. So no more surgeries. They're trying to like get rid of their surgeries. So people like you, when they build a very strong, fast sequence detectors in a circuit level, that will help to build devices, and these devices will be giving a fast reaction. And instead of taking 1 day or 2 days from CVS and, you know, Walgreens to tell you whether that you're a positive case or negative case, if you can do it in 2 minutes, that would be great. If you can do it in 0 time, that would be great. And who will be responsible in this building circuit like you engineers? So that will be a part of the finite state machine examples after we finish the counters and registers. Anyway, we talked today about, you know, there is up counter, down counters. We'll figure out based on how many flip-flops we're representing how many bits, then, you know, what is reflection on how many states we have. Then we give example about, you know, if you have a 3-bit, that means it's gonna be 3 flip-flops. That means, you know, 2 power 3, 8 states. And, you know, based on the behavior of the counter, whether it's up counter or down counter, the state will be sorted. If you up counter, you're gonna be 0 to 7. If you are down counter, that means you're decrementing from 7 to 6 up to 0, and you will ring back to 7. There is other type of counters, it's called modular counters, which is basically, it doesn't need to be covering all of the state that it will be covered by number of bits. You can pick up any number in the middle and truncate, and that will be resetting and neglecting the rest of the states the number of bits can cover. Then, you know, we start talking about synchronized, asynchronized, and we said synchronized is basically every single element in the circuit as a sequential element will be using the same source of clock to running and monitoring the events, which can happen in the positive or the negative edge of the clock based on the behavior of the counter itself. Then we're starting with example about design level, using all of the information about the state table on a finite state machine graphical representation, ending to a real implementation. And we were taking the use case of the 3-bit up counters. And we looked to the up counter without any control, just with the clock. And we made the state machine, and we know it was really easy peasy lemon squeezy to get the Boolean algebra and build a circuit. And then we moved the gear in implementing an extra control, which is called enabling, by resuming the movement from a state to the other, or like staying in the state itself when the polarity of the signals will be changed, considering this as an external input. Then, you know, we build the table. We said it's gonna be like a self-homework for you to practice by filling the excitation table of the 3 different consecutive flip-flops. Then, you know, we move the gears into the, if we have a reset, and what is the reset and what will be the effect of the reset on the finite state machine for the same problem we solved with enable. And we already made it here, and it was fancy as you can see. And then we said, you know, you guys will be able to fill the state table and make the full implementation, but this time just to practice to use another flip-flop, which is called D flip-flop. Last thing, recommending for counters is to use the T flip-flop, while building registers and memories is to use D flip-flop. But it doesn't mean that is a Bible. You know, we are designers, so that means I can change at any time I want. We finished today. If you have any question, let me know. Any question? Hello?
No, it's great. Thank you.
Okay, so in that case, I want to thank you guys for attending the course and attending the class today. And I wish you guys the best of luck and the best of the great day today. And also, I will see you on Wednesday. God bless you. Please stay safe. This is the most important thing. I'll see you on Wednesday. God bless you. I'll do my best to grade. And I hope all of you guys will pass with A, hopefully. Okay?
Wait, Professor, real quick. For your robotics competition, do you require anything? Do you need like
coding? If you love into learning coding, do you like to build robots and stuff like that?
Yeah.
Yes, sir.
Okay, so if you want, give me 1 page telling me what you already have done and how quick you can learn, because I need people from all levels, from the 2,000, 3,000, 4,000, so I can build a very strong team.
Okay.
They're gonna give us like a $6,000 if we're gonna be selected to build the robot.
Do you have like a Google form, or do you want me to just email it to you, like the one page?
That's a very good question. So what we can do?
I can make you one. Google Forms.
Can you make one and share with everybody and on the Slack?
Yeah, I got you.
Okay, put it in the Slack, then I can see what's going on, and you guys will send me also your resume, and then I can sit and read it. And if you guys have any question, please let me know. And I hope that you guys will join. That's really fun. I can have a big team.
All right.
Okay, thank you guys. God bless all of you, and I'll see you on Wednesday. See ya.
Have a good one.
You too. Thank you. Bye-bye.